point should be in a single cluster. Okay, that is C1. And then what you do, remove a cluster from the list of clusters. So list of cluster, it had only one, so you remove it. Now there is no cluster. And then that means entire data set, in first phase you take the entire data set and apply the k-mean clustering. What is the value of k here? K equal to 2. Okay, k-mean clustering means here you have to bisect the selected cluster using k-mean clustering method for a number of times. Okay. So now what you do it, you got the many results, okay, coming from each k-mean. So you apply k-mean on the same data set, you got result. You apply again k-mean on the same data set and you apply the results. You came in with the same data set, apply the results. So 10 results you got, and for each clustering has 2 clusters. Okay. Now what you do is select 2 cluster from a bisection with lowest total SSE. And for each clustering, okay, you compute the SSE and you choose the any one of the many clustering. That means you have 10 clustering. Each clustering has 10. Each clustering has 2 cluster. Okay. And then what you do it, you choose one clustering. Okay, where SSE value is minimum. Select 2 cluster from a bisection with lowest total SSE. Now you add this clustering to the original list of clusters. So this cluster has 2 cluster. So then you add it here. Now earlier you remove it, so it was null. So now you have 2 clusters. Okay. Now among these 2 clusters, again you remove a cluster. Now which cluster you should choose? I don't know whether I said in the last class or not. You choose a cluster where SSE value is maximum. Okay. Among these two one, you choose a cluster where SSE value is maximum, or you choose a cluster that you choose a cluster for which the number of point is more than with compared to the others. Others mean with compared to all others. There is a logic behind it, because if a cluster is much in higher size, so it's very likely actually it consists of 2 or 3 more subclusters. So that is why after choosing the for initially you need to remove a cluster which has the number of points more or SSE value is also more, because if you have n points, you have n cluster, so SSE value will be 0. What is objective? Objective to have the minimum SSE value. So therefore you choose a cluster which has maximum SSE value, so that if you split it at the end of the day, you will get the minimum SSE. Okay. So therefore what you do it, again apply the same thing only for that cluster, that is out of 2 you choose 1. Okay. And again you do the same thing and again you will get the 2 cluster. Now you add these 2 cluster here. So earlier it was 2, you remove it 1. So it had 1 and then you add it here. So now you have 3 clusters. So out of the 3 cluster, what you do? You remove 1. So now you have only 2 clusters and you have removed here. So again this cluster will form another 2 clusters. So you add these 2 cluster here. So you will get the 4 clusters. Now out of the 4 cluster you remove 1 here, so you have 3 clusters and then you are working with 1 more cluster. From this cluster again you will get 2 clusters. So these 2 cluster you added here. Earlier it was 3 and now you added 2, so 5. So that will be the final output. Is it okay?
So when we bisect a cluster after the removing the cluster from the list, so basically we are doing the like we are taking k is equal to 2 all the time.
When you apply the k-mean clustering, k is always 2.
Yes, sir. Yes.
Okay. In bisecting k-mean,
Yes.
actually k is always 2 here. Okay. But number of cluster is different issue. Number of cluster can be anything. See, in k-mean also number of cluster can be 10. Here also can be number of desired cluster can be 10. Okay. But each page we apply the k-mean clustering where k equal to 2.
Yes, sir. Thank you, sir.
Yeah, someone has started recording. Okay, it's no issue. But I think someone has to share the recording among yourself. For my end, it's not recording required. It is already recorded, so I will share it. Okay. So you have any question still?
Sir,
Yes.
sir, why only two came in at each bisecting? Any reason for that?
Why two? Why not
Yes,
more?
sir. Yes, sir. Why not three? Why not four?
Okay, one simplest answer, initially the algorithm itself name is bisecting came in. So therefore each time it is suggesting that you should go for the two clusters. Okay. Algorithm name is bisecting k-mean. This is one issue. Another thing is, see, you know the k-mean. Okay. So this is a variant of k-mean. So now if you take the k value is above 2, so you can take any value of k and you can run the many times and you choose the best one. Okay. So same way you can do it, but only problem is the, say, converging two clusters and converging say multiple cluster, it will obviously there will be a implication of the what is called is like complexity. This is another point. And then can you tell what will be the value of k? Say why they are taking is what is the ultimate aim? Ultimate aim to reach k number of cluster. So at the single stage, if you take k equal to 6 and then you got the 6 cluster, so then there won't be any difference from the original k mean and this k mean. And then if you can apply the with different values of k and you can choose the best one. So that also there is won't be any difference from the earlier approach to this approach. So why they have taken this is actually it's not a partitional clustering. This is a hierarchical clustering. So every time you choose a cluster which has the minimum SSE value and then you keep on partitioning. Okay, earlier also I said key because of that actually it is giving much better results than the earlier case. So in summary, bisecting came is always one cluster it choose and it divided into two. Okay. So if we apply many clusters, so like k-mean, so there won't be any difference between original k-mean and this k-mean.
Sir,
Yes, go ahead.
sir, regarding the last question that he asked, like if why like if we apply some k value more than 2 also,
Hmm.
all values of k won't be reachable by that, right? Because if k is 2, only then we will be able to increment the number of clusters by 1.
Hmm. Now, what was the first question? K will be incremented by 1. That is why I understood. What was the first question?
Sir, I told that the last question he asked that why we select k is equal to 2, not k
Hmm.
is equal to 3 or 4 other things. You told
Okay.
that we can also do that, but it would be normal k means cluster. But
Yes.
I think there is another one, maybe like just saying that if we select some k,
What is happening? Is the internet fighting or something?
okay. So sir, I'm saying that if k value is taken to be 3 or 4 or something like that, we
Mm-hmm.
won't to reach all values of k by that, because by k is equal to 2, we are able to increment the number of clusters by 1 only.
Mm-hmm. No, that is okay. Why one? But if you take instead of k equal to 3, okay. If k equal to say 3, so what is the objective? Objective, so let's say we have to find k equal to 5 clusters. Okay. So if I take the, instead of k equal to 2, you apply k equal to 5 at the first stage. Okay.
Okay.
We can do, right? We can do it, right?
Yeah.
With
Yeah, in
k
that
equal to 5. Okay. So then what is the difference between original k mean and this k mean?
Yeah, correct. Yeah.
And then k equal to 5, and then you do the many times. Okay. Say they said also you do the many times. Here also you can do the many times. So is it like you apply k mean with different initial point and you choose the best one. So there won't be any also much difference from the original k mean and this algorithm. So why it is
Yeah,
like
correct.
hierarchical clustering actually always better than the any other flat clustering. We'll study the hierarchical clustering because here each time we are getting a different clustering and then we are choosing the best one. Okay. So obviously there are density based clustering algorithm top of the all. So that give much better with compared to traditional partitional and hierarchical clustering that we will go through. So in summary, answer is okay. We said k equal to 2. Obviously, you can take the value more than k, but there won't be much difference from the original k mean. And it is proven that bisecting k mean is much better than the original k mean. And people started using bisecting k mean instead of original k mean. Okay.
Okay.
So I just uploaded the last day's video. So maybe you can see it. I think I need to do some pre-processing again. Yeah. So that I'll do it. So now where from should I start? So this is bisecting k mean, we cover it. And then optimization part also you understood hopefully, right? So base for that case video will be the best because we need to write many things here. Is it okay for k mean as a optimization problem? Anyone is having any doubt? No doubt. So no doubt that you didn't understand or what? Or no doubt that you really understood? Which one is correct? Chinmay, respond. Someone should respond. Someone should be. Who is the?
Yes, sir.
By
Yes,
the-
sir. Yes, sir.
Who is the volunteer? Who is the what is called is seer? Does he belong to this class or some other class? Or there was no election because of the
Groups are different.
Huh?
The groups are separate, so like there is no defined CR. Like I don't think.
No, that is fine. But who is the seer from BTech? BTech students are majority here, I say.
Million thing.
You don't know. You don't trust on democracy.
The Milind is there.
Huh?
So Milind is there.
Milind is here in this class? Acha Milind, okay, I remember his face. Okay. Acha, by the way, say in the early morning, I don't want to spoil just chatting. So came in an optimization problem. Hopefully you understood. So next we move to the another part is something called triangle inequality to accelerate came in. Okay, so I think should I run the video and then if you have a doubt, I clear it? Or which one you feel comfortable, video or say direct interaction?
So the video is also interactive.
Video is also interactive. How do you interact with video?
I mean, what means you are also like giving writing in pen on that, and then giving example and showing. So that is also good.
So is it Onimesh or what?
Yes, sir.
Okay. Okay, so then I run the video for this one. And if you have any doubt, actually I am here. So if you have any doubt at any point or after end of the video, you obviously raise your question. Okay. So I am not cheating, so I am here. Okay. So therefore, what I can do it, yeah. So I must share the video here. Let me see. So obviously, if you have any doubt, please let me know. So in last class we talk about clustering approach. So that is the part of. No, I think I missed the video somewhere. So I have to start the different. So I have to start the last day's video. Yeah. Here, and you have a set of points here. Yeah. You choose a point. So I am here. If you have any doubt, please let me know. On the left side, there will be, on left side and right side, there will be equal number of points. If you assign the points in that way. So in the other way around, so this is nothing but the median of the all data points. Let's say example 1, 2, 3, 4, 5, 6, 7, 8, all are 6. These one. So 5 minus 9, it will be minus 4. Similarly, this will be plus 3, this will be minus 3, and so on. So ultimately, what you will get, this is the original values. Ultimately, this represents that this is nothing but the median of the distribution. So median of the distribution is nothing but the, if you take the multidimensional, so it is nothing but the centroid. So next we will talk about something to speed up the k-mean clustering algorithm. So if we move back, k-mean clustering, if you see here, k-mean clustering. So what we found in k-mean clustering, we initially choose some set of points here. Okay, that is the initial k point. And now for the all set of points, we compute the distance from x1 to the this centroid, this centroid, and this centroid. That is we do. And wherever the distance is minimum, we assign to the closest cluster. That is the k-mean algorithm. So initially you take the k centroid and we compute the distance from the each point to the k centroid point. So therefore, how many distance we compute? So if there are n number of points, for each point we compute the k distance. So therefore, in single iteration we compute the distance into k. K is the number of clusters. Now, Elkin in 2003 paper published in ICML. ICML is one of the top conferences. Okay. Paper published, but idea is very simple. And he said there is no need for doing computation from the point, each point from here to the all centroid. So let's say if we use the k-mean as a pre-processing step, you have a, let's say you have a say 10 million data and k value is say, let's say 1000, because you are using k-mean as a pre-processing step. You can consider, because this is not the final pre-processing. You will have a some sophisticated algorithm on the top of this one. So for each point, you have to compute the distance 1000, and then what there will be 10 million. So 10 million means 10 into 10 to the power 6, and then 10 to the power 3. So these many distance computation you have to do. He said, can you reduce the distance, number of distance computation? A number of distance computation complexity depends on the dimension. If you have 1000 dimension and you have a 2 dimension, obviously that will make a huge difference. So therefore, he focused how to reduce the distance computation in some scenario. That is the paper all about. So triangle inequality to accelerate the k-mean clustering approach. So he used the property of the metric space property. As you studied earlier, the metric space property means it satisfies 3 conditions. So distance function will be distance from x to x will be 0, and always distance of any point x to y greater than equal to 0, and it should be Symmetric distance from A to B is same as distance from B to A. Distance from Kolkata to Delhi same as the Delhi to Kolkata. And distance from A to B plus distance of B to C, A to B, B to C is greater than equal to distance from A to C. So that is something called triangle inequality. So what he said, we can avoid some distance computation using this theorem. How? Let's say here. So we have a point here, we have a centroid here, there are two centroids B and we have a point X. We are trying to find whether point will be assigned to B or C, any one of the centroids. So there will be multiple centroids. So we can generalize that. First we think of there are two centroids B and C and there are point X. So we computed the distance from X to B. We know this distance. And obviously when centroid is formed, this was also computed C to B. Otherwise we can compute the distance from B to C. So we know this distance here. Now we will estimate what can be the value of X to C without computation. Not only that, we won't estimate actually. What we conclude that if distance from B to C is greater than the distance twice of the distance from X to B, then this X cannot be assigned to C because distance X to B is much closer than the distance from X to C. I repeat this. There are two centroids B and C. We know the distance from centroid to centroid. And we computed the distance from X to B. We know this distance. Now challenge is, can we avoid this distance computation? If we can avoid, so if we go more for another points here, similarly, can we avoid this second centroid, say, let's say C1 and so on. So in that way, we can reduce the number of distance computation in K-means. So what if they said key, if distance from B to C is greater than the twice of the distance from X to B, then no need to compute this distance because this distance is greater than the distance from X to B. So the point X is closer to the centroid B. So we can assign the point X to B. So there is no need for computing distance from X to C. So just we'll compare this value. And this is pre-computed. So this time will be 1 unit. But if it is 1,000 dimension, so you need to have the 1,000 unit time for spending the time computing. That is their theorem. So how they got this theorem, that is we'll see here. So from triangle inequality, what we can write, distance from X to C plus distance from X to B. We can write distance from B to X plus X to C is greater than equal to distance from B to. We can write this one, distance from X to B plus X to C. So we write B to X instead of B to X to A, we write, I wrote it X to B, and X to C, we write distance from X to C is greater than equal to distance from B to C. We can write, there is no confusion from the triangle inequality. Distance from here to here and distance from here to here is always greater than the distance from B to C. Now simply distance from X to C plus distance of X to B is greater than equal to distance of B to C. What is the distance of B to C? You just simply replace. Distance of B to C is always greater than equal to distance of X to B. So we can write here 2 distance of X to B. From here you can write distance from X to C greater than equal to, you can take out it here. So then distance of X to B. So therefore, if you know this distance, you can compare. And if it does not satisfy, in that case, you have to compute the distance. There is no other choice. But if this satisfies, then you can avoid many distance. So do you have any doubt?
Sir, but this for this the K has to be very less probably. So for this to work, actually the k value has to be less than, because if it is more k, so you have to find the distance between more centroids. That will be more computations indirectly.
But that will be much faster than the original k-mean. See, for original k-mean, for each point you need to compute the distance. Here actually we don't need to compute the distance. We only comparing the distance. Okay. So computing distance means what? Say suppose if it is a d dimension, for each dimension you have to subtract and make it square. Okay. So therefore, if d dimension per unit is square subtraction, if it is 1 unit, so it will be take d. But here only we need to compare these two terms, whether this is greater than equal to no or not. Okay. Even though you are saying ki if k is value is huge, okay, k value is huge. See, k mean, if you only you want to use k mean, okay, then you should have an idea at the value of number of clusters. So number of clusters in a scenario, see, generally people apply k-mean. So when okay, k-mean can also be used as a pre-processing step. So whatever the situation is, if the value of centroid is also more, okay, it will be much faster with compared to the original k-mean. Is it okay? Or do you express different opinion?
So I was saying, like, if there are let's say four centroids, then in normal k means what we'll do is we'll find the distance of a point x to all of the four centroids. So we have to make four computations, but in this case we have to find the distance between all the centroids. So that will be I think six. So six distances, and also one distance from either up the x to one of the points. So seven distances we have to find and then compare minimum.
Okay, I notice your point, but you forgot one thing. Say that centroid to centroid distance is pre-computed. Okay, why it is pre-computed? Let's say what is centroid? Centroid to centroid distance. Centroid to centroid distance. If we once pre-compute, then there is no need for computing that for every time. So you are saying there are 4 points, 4 centroid, okay, and then you have a point, let's say x1. What you have to do? You have to compute. See, these distance are pre-computed. This is you are comparing only for a single points, right? So, but how it is benefited? You are saying how it will be benefited. Say, let's say this point. What you have to do? You have to compute 4 distances, right? 4 distances from one point to the all centroid. You are saying you have to compute 4 distances, okay. And similarly, for using accelerated k-mean, you have to compare only, not any distance computation, okay. This is one thing. Acha. And another thing, if you are saying for each time you need to compute from one point to another point distance, so it will be 4 into 3, that is you are want to say. So it will be 4 cross 4, and then it is a symmetric, so it will be what, 8 or 6,
By two.
right?
6.
So
Yes.
6. So it will be 6 distance and then 4 comparison. But in earlier case it will be 4 distance. That is your point, right?
Yes, sir.
So this is you are comparing for single point. Now if we have a 100 points, let's say in a data set, okay. So then what will happen? So this 6 computation, whatever you did, no need for repetition of this part. Okay. So only what you have to do, you have to compare 4 into 100 comparison, wherever for earlier case 4 into 100 comparison plus 6 is initial centroid computation. Okay. So and for all other cases, so there are 100 points and you have to compute how many distance, that is 400 distance. So if you have 100 points, then you have to compute 400 distance. However, if you use accelerated k-mean, so you have to compute the so let's say 6 original distance computation and then 400 what is called is 400 comparison. Okay, and apart from if this comparison fail, obviously you have to compute the exact distance. This is the difference. Okay, so in original K-mean always you are always computing the distance, and each distance computation, if it is a d dimension, so it will multiply with d. Okay, but here if you use the accelerated K-mean, so only the 6 into d and then rest of the all are comparison. So if you take into consideration the dimension of the data, obviously that this accelerated K-mean will be much faster. And this is very small data set. Instead of say, let's say, even it may happen you have only the 4 centroid and then 1 million data. So you just multiply 1 million into 4. That will be the number of distance into d. That is the set features. It should be compared with the 1 million comparison and say initial, say let's say 6 distance. Okay, so in that case obviously the accelerated K-mean will be much faster than this one. Obviously you cannot tell ki because there is no surety that no cases you need to compute the distance. Some cases obviously if it fails then you need to compute the distance. Okay, so therefore complexity point of view, asymptotic complexity will remain same for the both the algorithm accelerated K-mean as well as the original K-mean. But if you see the time, so obviously this will be much faster than the original K-mean.
Yes, sir.
So any other observations? So this is so simple, but paper was published in ICML. Can you imagine? ICML is a really great conference. So along with that, there was another theorem. That theorem is also much easier. Okay, to further refine the what is called is distance computation. So you just imagine. So if you think over it, maybe simple idea can also be published in a top tier conference. So that was in 2003 by single author Elkin, Charles Elkin. Okay. So now I'll talk about hierarchical clustering. Okay. So I prefer to run the video, and then if you have a doubt, we can go for discussion. Okay. So therefore, I am sharing the video here. So in last class we talked about K-means clustering approach. So that is the part of partitional clustering approach. As I said, there are many clustering approaches, and this clustering approach can be classified into two main categories. One is partitional clustering, another is the hierarchical clustering. Partitional clustering create a flat clustering or a single clustering, whereas hierarchical clustering, it creates a multiple clustering, a sequence of clustering. Okay, so that is we will cover today. So hierarchical clustering method create a sequence of clustering, that is each clustering is denoted by pi1, pi2, pi3 and pi for the given data set. It can produce inherent nested structure of the cluster in a data. So like family tree, okay, so this is a hierarchical structure. So similarly, if in a data set there is some hierarchical structure, to capture that hierarchical structure, this clustering algorithm is the good idea to apply. Okay, so we move forward. This hierarchical clustering approach can be obtained as you understand that, as I said, it forms a hierarchy, and this hierarchy of the data or of the cluster can be formed in two ways. One is something called the divisive approach. Okay, divisive approach means you start with one cluster containing all the points. Say suppose you have 1000 points, so consider this entire data set is a single cluster, and then you divide the data set into two clusters, then from two clusters to three clusters. In the next cluster, you form another four clusters and so on. Each step split a cluster until each cluster contains a single point. So you started with, let's say, 10 points. Now single cluster, then you will have a two clusters. Obviously, number of points will remain same. That will be divided between two clusters. Now from 2 to it will form, let's say 3 clusters, and then from 3 it will form 4 clusters, and so on, until or unless each cluster contains a single point. So this is something called the divisive approach. So we talk about k-means variant, that is bisecting k-mean. So bisecting k-mean is a typical example of divisive approach. So you started with a big cluster and then divide into 2, and then next level you divide it into 3, and so on. Another approach, and that is the most popular approach, is called the agglomerative approach. What is that? So instead of considering the entire data set into a cluster, you consider that each point is a cluster. Okay, so start with the points as individual clusters, or mark the closest pair of cluster until only number of clusters become one. So it is on the other way around. I'll explain more detail. So you start with individual points in a cluster. Let's say there are 4 points only. So you start individual points in a cluster, and then what you do it. So start with the point in individual cluster, mark the closest pair of cluster until the number of cluster become 1. Okay. So then you mark this one. So let's say you merge this one 2 and then become 1. So all points become a single cluster. So here one example here. Say we have initially the points. There are 5 points: P1, P2, P3, P4, P5. So each individual point you consider this is one cluster, this is another cluster, this is another cluster, this is another cluster, and this is another cluster. Okay. So this is a clustering where each cluster contains a single point. This is one clustering. Now you move it. So P2, P3 is merged. So P2, P3 will form a cluster and all other remain same. This is another clustering. Now in the next step you merge with P2, P3 with P4. So P2, P3 will merge with P4. So this is another cluster and this is another cluster. So this clustering, this is another clustering. So it has 3 clusters. Now you merge with P2, P3, P4. This is one, and another is you merge with P1 and P5. So you merge with P1 and P5. So there are 2 clusters. Now you merge these 2 clusters, you will get a clustering. So let's say pi 5, and that consists. Oh, it is already there. So pi 5 will form the single cluster. As you can see, this is a cluster, and all points here. So if you see from the down to up, this is something called the agglomerative approach. Now same thing you can think of. So initially it has all points are in a single cluster. So this is the number of cluster is here 1. Now this cluster divided into another 2 clusters. So let's say pi 5 to pi 4 another cluster. So P1, P5 in one cluster, another is P2, P3, P4 is another cluster. So here number of cluster is 2. Here number of cluster is 3. Here number of cluster is 4, and here number of cluster is 5. As you understand, last one and the first one is trivial. Okay. So there is no need to do anything. But in between, you need to have some algorithm to partition the data. A systematic approach. But in general, what happened, actually divisive approach is not very popular. On the other way around, the agglomerative approach is popular. What is the agglomerative approach? We start with individual point in a cluster, and then we merge the clusters, and then we reach to a situation where number of clusters is 1. So therefore, we only study the agglomerative approach. So next, we will see how agglomerative approach works. So here, this is something called the bottom up, because each individual point was in a cluster, and then we merge these 2 closest clusters, and then maybe we can merge these 2 closest clusters first, and then this one, and then you merge it here, and so on. Okay. This structure is something called the dendrogram. As we have seen earlier, this structure is called the dendrogram. This tree-like structure is called the dendrogram. This is the output of the hierarchical clustering approach. Now we will study this algorithm, that is the agglomerative approach, very carefully. Okay. How do we proceed? We will be given the data set without label. That we know, that is because we are talking about the unsupervised learning. Okay. So what is the first step? Compute distance matrix for the data set. What is distance matrix? Suppose in the data set you have the point, let's say P1, P2, P3, P4, and P5. So you have 5 points. So what is the task? Task is to find the distance matrix. So distance matrix is nothing but it represents the distance from one point to the all other points. So that I think I covered in somewhere here during the class of the data. Distance matrix I probably told. So here there are 5 points. So then from each point to all other points you have to find distance. You have to find the distance. So we compute a matrix of size, because there are 5 points. It is a square matrix of size 5 cross 5. Okay. And what do you do it? So from point P1 to all other points P2, P3, P4, P5, we find distance. Distance from P1 to P, obviously it is 0. So similarly P2 to all other points you find distance, P3 to all other point distance, P4 and P5 and so on. So this is something called the distance matrix. So first step is done. Compute the distance matrix for the data set. Now let each data point be a cluster, because we are considering the agglomerative approach. So agglomerative approach that we learn is each data point will be considered as singleton cluster. So if there are n points in the data, so then at the first step you will have the n cluster. Now this is important. What is that? Merge two closest clusters. You merge two closest clusters and update the distance matrix. This distance matrix basically represents the distance from, I said 1 point to 1 point to all other points. This is right. It is not only that, this distance matrix represents the distance from one cluster to all other clusters. Once I said each point is a cluster, so please note that each point itself is a cluster. So this distance matrix itself represents the cluster to cluster distance. From one cluster, say P1 is a point as well as a singleton cluster. So distance from P1 to the all other cluster is represented. Similarly, P2, P3, and P4. So, and we have to repeat this step. What are those steps? Merge at each step two closest clusters. So at each step we are merging two closest clusters. That means each step we are losing one cluster. So initially there are n number of clusters. So when you merge two closest clusters, so this will be 1. So therefore number of clusters will reduce to n minus 1. So next step it will be n minus 2, and next step it will be n minus 3. And then you reach a point where the number of clusters is 1. So that is the agglomerative approach. So what you do it in this step, merge the two closest clusters. This is very important, the two closest clusters. And second step, the update the distance matrix. Distance matrix will represent the distance from one cluster to another cluster. After merging two clusters, there will be change of the distance between one cluster to others. So therefore, you have to update the distance matrix. Merge the two closest cluster. How do you find? So you have to search the matrix, and you have to find the wherever the least entry, and then that entry is nothing but the distance between two clusters. Okay, there are some advanced methods, but this is the way we can do. So what is the, then in summary, what is that? Compute first, you compute the distance matrix. Each point is considered as a cluster, so this distance matrix itself represents the distance from one cluster to other cluster, and then you go repeatedly, you do for the n minus 1 times, Each time what you do is you merge the two closest clusters and update the distance matrix. So here, if you see the original slide, so there is a mark closest cluster. How do you find the two closest cluster? And obviously update the distance matrix. So we have to understand these two parts very carefully. So how do we merge the two closest cluster? Before knowing the how to merge the two closest cluster, closest means minimum distance cluster. That is obviously it is known. But before that, we should know how to compute the distance from one cluster to another cluster. We know how to compute the distance between 2 points. Okay. So using Euclidean distance, we can compute. So, but thing is that how to compute the distance from one cluster to another cluster. Each cluster consists of a group of points here. You have also a set of points. How do you compute distance from cluster C1 to C2? So that will be the distance between one cluster to another cluster. So different way we can compute the distance from one cluster to another cluster. So this is the way. There are three major ways that we can compute the distance, and each technique is something called if we compute the distance in this strategy, then we say is that agglomerative approach we say is the single link or single linkage approach. If we compute the distance in this fashion, then we will say that agglomerative approach is called the complete linkage method. Otherwise, if you compute the distance in this fashion, then we will say is that agglomerative approach is the average link. So there are three algorithms. One is single linkage hierarchical method, another is complete linkage, another is average linkage. Only you change the distance measure, otherwise basic structure of the algorithm remains same that I covered in the last slide. So what is the distance from one group to another group? So this is the single linkage distance. You have the points here, you have the another points here, another cluster. What will be the distance between two clusters here? Distance is nothing but the distance from the two closest point. From each point is taken from the different clusters. So then what you have to do? You have to compute the distance from this point to the all other points. You have to compute distance from the all other points. So you have to compute one point to the all other points distance. And wherever the distance is minimum, that will be the distance from the two closest clusters. So that is something called the single linkage algorithm. So more mathematical, it is the minimum of the all distances here, where each point is taken from the different clusters. So next is complete linkage or complete link. Complete link is just opposite of the single link. It is the maximum distance between the 2 points. So here it is minimum, here it is maximum. And next is the average link. What is average link? You compute the all pairwise distances from this point to the all other points. You compute the all pairwise distances and you take the average distance. Average, if there is n points and n points, so how many distances you have to compute? M into n, and you take the average distance. So from one cluster to all other clusters. From one point to the all other points, from one point to the all other points, you sum up and you take the average. So that will be the average. Basically, I taught three algorithms. One is single linkage, another is complete linkage, another is average link or average link. But you have to remember the previous part. This remains same. So suppose if I ask you apply the single linkage or complete linkage or average linkage, these steps will remain same. So in first step you have to compute the distance matrix. And then each data point will be clusters and you merge the two closest clusters. So closest cluster means what? So you have the distance matrix here. So you find the two closest clusters. Yeah, so this is the minimum distance. Okay, and you merge these two clusters. Now when you update it, you update the distance matrix according to the distance formula. When you merge it, always you choose the closest one. There are two differences here. When you merge the two closest clusters, it is irrespective of the any algorithm. Always you take the minimum distance cluster. But when you update the distance matrix, that time you have to compute the distance from one cluster to another cluster. And then you have to choose if it is a single link, you take the distance from the 2 points. two closest point. If you consider the what is called is the complete linkage, you take the farthest distance. So one example I can give you here. Let's say you have a point here, 1, 2, 3. You have a point here, 4, 5, 6. Now instead of that, if I say here this is 1 point, here 1 point, and let's say here you have point here, and here also you have a point here, here, here. Now if you use the single linkage, what will be the distance from two clusters? It is the distance cluster from C1 to C2. If you use the maximum, if you use the complete linkage, so this will be the distance. So let's say this is the farthest point. Okay, so that will be the distance. Okay. Now you have another cluster here. So let's say here. So from here to minimum distance will be here, and let's say minimum distance will be here. So we are considering let's say single linkage. Okay. Let's say this distance is 2, this distance is 1, and this distance is 3. Now you have to mark the two clusters. So which one will be marked? C1 and C3, because this distance is minimum. Okay, so this is a single linkage algorithm, but always it is irrespective of any clustering approach, always you choose the minimum distance. One example, if I say again, let's say you compute the complete linkage. So the complete linkage distance, this will be let's say 6. From here to, so this is the 2 point, let's say this will be the farthest one. So this will be 5. And this will be the, let's say, farthest distance. So this will be, let's say 5, 4, 3. Okay. Now which cluster will be merged? Among these distance, you have to find the minimum closest one. So which one is to be merged? So this C1 and C3 will be merged. While computing distance, you use those formula, but when you merge the cluster, you have to choose always the minimum distance. Not the you have to merge C1 and C2. That is not the right, because it is said the merge the two closest clusters. Now we'll talk about the complexity. So what will be the complexity for the agglomerative approach? What is the step? Compute the distance matrix for the data set for one to one other point. So complexity will be order of n square. So forget the space complexity. So time complexity is order of n square. Okay, so for this one it will be order of n square time complexity, and space complexity also will be the order of n square, because you have to keep them in the matrix. Now this is the step. Until first one point, so there are n cluster until a single cluster. So then how many, this step, how many times you do it? N minus 1 time. And then what you have to merge the two closest clusters and update the distance matrix. So how many times you merge the closest cluster? N minus 1 time. And what is the complexity of merging? If it is n, then we say the total complexity is order of n square. If it is n square, how do you merge? Find the two closest cluster. So if without any further data structure, what you can do it? So you have to merge the two closest cluster. How do you merge it? You have to find the all elements here. So there are order n square element, order of n square element. So searching a minimum point, it will take the order of n square time. Okay. So each time you have to find the minimum. So order of n square time. So for this step itself, will take order of n square time. And what you have to do? You have to update the distance matrix. Again, distance matrix at most it can take a order of n square time, and this has to be done for n time. So therefore, complexity will be order of n cube if you don't use any other data structure. Here we say the time complexity is order of n square. So I stop at this point here. Okay. So tomorrow we will discuss some other algorithm, how to reduce the time complexity from order of n cube to order of n square. Okay.
Yes, sir.